have a term for it. Summer melt. Students who just decide not to come. Okay? And they allow for that. Okay? If any of you are trying to decide whether to go to a university you're not really that interested in versus staying at Cabrillo or going somewhere, if you have any questions, well, welcome you guys. If you have any questions about where you should go, or should you stay at Cabrillo another semester or whatever, I can help. So just come and see me. Also, I have contacts at all the universities, so if there's any question that you have about your application or whatever, come and see me. So I'm your resource if you need me. Okay? All right. And those of you who have one more year at Cabrillo, come and see me and make sure that you're lining up to take the right classes next semester. I think that tomorrow might be the first day of registration, and some of the classes fill up quick. So if any of you, is tomorrow the first day? Anyway, it's coming up. It's coming up sometime. So any of you who are planning on staying, come and see me, and I can check to make sure that you are planning on taking the right classes. Okay? Anybody have any questions regarding just engineering and transferring courses? No? Okay. How many of you are transferring? Okay. I passed this around on Tuesday regarding when you could take that 4th exam, and some of you signed up for Wednesday at 6, bless you, great, and some of you signed up for Thursday at 6. So whichever time you signed up for, show up at 6, and it's going to be in the engineering lab, engineering 810, okay? So 6 o'clock. So it's an hour and a half final. It goes from 6 to 7:30.
For Wednesday and Thursday?
Wednesday and Thursday. If you sign up for Wednesday and you want to come Thursday, don't email me. Just show up on Thursday. So basically, some of you are taking it in the proctoring center, so you take it whenever you want. Some of you signed up for Wednesday. Some signed up for Thursday at 6. Just show up one of those times. And you don't have to tell me which one you're coming, and you don't have to tell me if you're switching. But everybody got it. 6 o'clock, because I wrote on here 6 to 9. No, you don't need 3 hours. 6. 6 o'clock. Everybody hears that, right? What time?
6.
6. In where? The engineering lab.
The AM or PM?
PM.
AM for you.
Okay.
Yeah.
1800.
Um,
If we're going to be engineers, we might as well.
And Brandon, I just emailed you when you're doing it, and I bet you're going to let me know. Taking it. Okay, so I don't know what's up with this screen, this thing, so we're going to just kind of do this one. Yeah. Oh, yes, the final time. Yeah. Final time. So it's set up for us Tuesday morning from 7 to 10. And the yawning is very representative of 7 to 10. Does anybody have a final on Tuesday at 10 o'clock? You guys don't know. Does anybody have a final? You don't know yet. Well, we're going to have to decide.
What day is that?
It's the week of finals.
I know, but it's
The 16th.
no. I want to do it at 7 a.m. on the day where it's
It's the 16th.
How about that?
Yeah. This guy.
It's coming right up here. It's the Thursday.
You know what, it would be better if it was Tuesday though, because I have to turn in grades on Friday. So I hate to get, those of you who are taking it, you guys, Charlie, those of you who are taking it in the proctoring center, the final exam in the proctoring, do you want to take it in the proctoring center, or could you take it with me? Proctoring. Okay, I would like you to take it on Tuesday or Monday or Wednesday, because I want to grade them all at the same time, and I don't want that delay, you know? Okay, so, syllabus. Everybody, syllabus? I have all the dates in here, and we put all the homework due dates. I posted all the solutions to the homework. So all the solutions are posted up on the website. Okay. Questions about the course in general?
No.
I'm willing to look at your project stuff if you have some drafts for me to mark up. It's due on Thursday, and the presentations are on Thursday. But if you have something, you guys listening? If you have something from the project ahead of time, drawings, analysis, whatever, give it to me ahead of time and I can mark it up. And then it'll be more correct when you turn it in. Okay, so on Tuesday we looked at centroids. What's centroid a function of? Area or volume. So it's a function of geometry, right? If it's 2D, it's area. If 3D, it's volume. What is center of mass a function of? Mass. What's center of gravity a function of?
Weight.
Weight. Okay? And just to zoom in here, when we were looking at center of mass, what did we sum up?
Summed up the forces.
When we did center of mass, we summed up the masses times the distance to the mass and divided it by the sum of the masses. Everybody with me? Okay. So when we were dealing with center of mass, which we knew the critical component was mass, we summed up the masses times the distances to the centroid of the mass and divided it by the sum of the masses. What did we do if it was center of weight? I mean center of gravity. What did we do? We summed up, it's supposed to be W, we summed up the weights times the distances divided by the sum of the weights. What if we did centroid of area? What did we sum up? We sum up the areas times the distances and divided by
Area.
the sum of the areas. And what about centroid of volume?
Same, but with volume.
Volume. We summed up the volumes times the distances and divided by the volume. Now, the last thing we talked about in class was the idea that there is something referred to as moment of area, moment of volume, and moment of
Inertia.
mass. And how did we find the moment of area? What, do you remember what it was? It was the sum of the distances times the areas. What is the moment of volume? Sum of the distances times
The volume.
the volume. Capital V, right? Because little v is what? Physics. Velocity. Okay, and what was moment of mass? Sum of distances times mass. Is everybody with me? Okay. So when ordinarily the term moment to us means what? What times what? A force times a distance, right? So if you sum up all the forces and multiply it by the distances, you have what we know as the moment, right? Force times distance. But in statics, even though to us the term moment means force times distance, in statics there's another use for the term moment. And it's moment of area, which is the sum of the areas times the distances. Moment of volume, which is the sum of the volumes times the distances. And the moment of mass, which is the sum of the masses times the distance. Everybody comfortable with the terminology? So there's moment of area, moment of volume, moment of mass. And And what is it? It's the sum of that critical component times the distances. Okay. The other thing we looked at, very last thing we did, is we talked about what it was referenced to. So if I'm looking at a two-dimensional problem, which is area, and I'm trying to find x bar, I'm referencing my moment of area is referenced to the y-axis, because here's my x-axis, here's my y-axis, and here's my body, and I'm measuring my x bar from the y-axis. So it's a moment of area reference to the y-axis. Talk to the person next to you and make sure both of you are comfortable with that term.
I haven't felt comfortable since the semester started. Sorry, Dad, Mom.
So when you're working on a two-dimensional problem, and you're solving, here, you guys look up here for a minute, is what I boxed in here the moment of area? No. Great. What is the moment of area? Only the numerator. The sum of the areas times the x's. And because we're trying to find x bar, and x bar is measured from the y-axis, it's the moment of area reference to the y-axis. How about y bar? When I try to find y bar, it's the moment of area reference to what?
X-axis.
The x-axis, because I'm measuring my y bar from my x-axis. Is everybody comfortable with that? 2D? Shake your head yes if you are. Okay. So now let's look at 3D. When I have a 3D problem, x, y, and z. When I measure my, what do you usually like? You usually like x here, right? Y here and z? Okay, so let's do it that way. So if I'm measuring my x bar, the line along the x-axis, the distance, the body is out in front of us. The body's out here somewhere. And I'm measuring what x bar is, the distance to the centroid of that volume. I'm measuring it from what? The plane, the YZ plane. So, the moment, and when I'm trying to find x bar, I'm finding the moment of volume reference to the YZ plane. And when I'm trying to find y bar, it's the moment of volume reference to the XZ plane. Is everybody comfortable with that? I mean, you need to understand that terminology that's used. Okay. These moments that you're finding when you sum up the areas times the distances, or sum up the volumes times the distances, or sum up the masses times the distances, they are actually called the first moment. The first moment. We're going to do that in a minute. So, did we solve any of these problems with integration? No. You've actually done integration with centroids already, in physics and I think in math. Okay? I don't think you did mass, but you did do area, I know that for sure. And I think you did 3D centroid problems, right? Was that math or physics?
Yes.
Okay, both. Okay. So you used integration, but the point when you get to engineering, we're not dealing with integration now. The focus is really composite body. Like, hold up your widget thing. So Margie has this thing, it's made out of one piece of metal, but it actually has more than one geometric design. So when we try to find the center of mass, or the center of gravity, or the center of area, or the center of volume of that, we really need to treat it as different composite bodies. And that's our focus as engineers. When you take a bicycle wheel, it has the wheel on the outside. It has the frame. It has spokes, if it's one of those traditional ones. It has 3 different kinds, 3 different bodies. And actually, you could include all the spokes as separate bodies. So for engineers, we need to understand how to calculate this when it's more than one body, okay? And you can do it by integration, but you gotta do it integrating each different thing. But in our case, we're just doing it using this. So when I sum up the volumes, the areas, or the masses times the distances, what is it called? The moment of area, moment of volume, moment of mass, right? Or, what is it really called? The first moment. The first moment of area, the first moment of volume, the first moment of mass. You won't hear people say that it's the first moment, but you know when you learn something for the first time, you kind of want to learn it the right way so you know what the terminology is going to be. So it's important for you to know that it's the first moment of area, first moment of mass, first moment of volume. And the reason why it's called the first moment is the integration has only a distance in it. It's the integral of x dA, the integral of x dV, the integral of x dF. Notice dm is for mass, dA is area, dA this is volume. That's why it's called the first. So mathematically speaking, with integration, what do you think the second moment looks like? So second moment of mass. Take a guess because it's right. Square. It can't be y because we're trying to find x bar, right? In the end, I'm trying to find x bar, so it has to be all the x's. So this is what the second moment of mass is. What's the second moment of area going to be? And the second moment of volume is going to be?
X squared
Right.
E.
Okay. Everybody good so far? Okay. What is the second moment of mass called? Moment of
Inertia.
Write that down. The moment of inertia is really the second moment of mass. The second moment of area is called just that. The second moment of area. However, in industry, in engineering practice, this is also referred to as the moment of inertia. Is it truly having to do with inertia? No, because inertia has to do with the distribution of mass, not area. But it's accepted. So a textbook, a statics textbook, will not call second moment of area moment of inertia. Because technically, the second moment of area is not the moment of inertia. The moment of inertia is what? The second moment of mass. However, so when you learn things the first time, they're telling you technically what it is, but then there's this jargon, right, or the lay terms that you use in industry, and you do call second moment of area, you also call it moment of inertia. For those of you who are civils, interested in civil or environmental or structural or architectural engineering, this is your baby. So civil, structural, environmental, architectural. This is your baby. Those of you who are interested in a mechanical, aero, biomedical, you have two babies. You need to be comfortable with both.
What about Chem?
This is all about structures,
Oh.
structural things. So when I use the word When I use the word structures, what do you picture in your head? A house, what else?
A bridge.
A bridge, what else? How about a skyscraper? Right? That's what you picture. But that's not truly what a structure is. A structure is anything that takes loading. Right? So a bicycle is a structure. Technically. It's taking load. It's not, it has rigidity. So anything that takes load, a bicycle wheel is a structure. Right? A space shuttle fuselage or a plane fuselage, that's a structure. Anything that takes load, takes force is a structure. So this is all about structural stuff, things that take loads. And it makes sense because this is called a mechanics class, right? First day of class I said mechanics is the study of bodies that are taking a load. And there's either static, mechanics is either considered static or dynamic, but both of them are taking loads. Okay? So those of you who are chemies, you know, it really doesn't, you know.
You're not.
What other majors are you guys? Industrials? You were the organized ones. Anybody industrial in here? Okay, you're organized. Okay, who's chemical? Charlie, are you chemical engineer?
Well, I might be environmental now.
You might be environmental, okay. So the only reason why I wrote environmental here is because environmental engineers might design, you know, wind turbines or something that has physicality, you know, and is taking a load. So what other majors besides these 7 I put up here in chemicals and industrials? Anybody interested in something else? Oh, electrical. Probably not in here, probably. Is there anybody interested in electrical in here? Okay, so Tim. So Tim, it's good that you understand this stuff because you're going to be working with mechanical engineers. Okay, so here on centroids, and I think you probably, I don't know, I'm thinking that you probably think this maybe is the easiest thing we've done. You think? Like on Tuesday when we just summed up all the, you know, we found a centroid or something by summing up where all the centroids are, and I don't know. It seems to me that this is probably the easiest. So transitioning from here to moment of inertia, it's not that it gets complicated, but it's weird. It's just not intuitive. So let's start with the intuitive part of it. And so let's look, and those of you who have the packet, you can pull out the packet. Here it is. Okay, so I think an important element is for you to really understand when do we use this. And I'm talking about only the 2 that are the most that are used. There is no second moment of volume. There is no second moment of weight or gravity. There is only a second moment of mass and a second moment of area. Okay? And these 2 things I mentioned, that they're called moment of inertia, and the variable that's used to describe it is I. Okay? And what is it? It's finding that second moment. So let's look at some instances in engineering that you actually use I, the moment of inertia. So one is, I'll give you civil and mechanical design. So beam design. So we're looking at a beam that's simply supported, right? It's supported on its ends and it has all this load here. If I look at, and this is looking at it from the side view, so remember back to orthographic views in Engineering 25, this beam is a rectangle. That's the shape of it. It's like taking a 4x4 or a 2x4. Okay? But then I could also use, not that, I could use this. What's this?
I-beam.
An I-beam instead. What's the reason for doing it? Well, let's say the outside geometry is the same. The reason for doing it is it's decreasing the weight, right? So that means transportation. material costs, transportation costs are decreased. But it also provides, so but it provides the same structural integrity that we need. So when we load this beam going down here, it starts to bend. And we talked about this at the beginning of the semester, that it's being stretched down here, so it's experiencing tension, and it's being squished up here, so it's experiencing compression. And we basically, in the end, by putting a force on here, it's experiencing moments on the sides, which you know now because we did shear and bending moment diagrams. But I want to know, those of you who took materials, what does a sigma, small sigma, represent? Stress. Stress is represented by sigma, and it's the force divided by the area. And stress is when you have a solid, and we talked about this at the beginning too, that the word pressure is also force over area, but it's only in terms of fluids. So air pressure in a tire, fluid water pressure in a pipe. The term pressure is only when you're dealing with fluids. Stress is when you're dealing with solids. When I put a load on here, I'm putting stress on it. I'm not putting pressure on it. Okay? So it's important for me to understand what is the maximum stress that it's experiencing on the bottom, and what's the maximum stress it's experiencing on the top. And it's the same. If both of these are symmetric, the stress on the bottom is equal to the stress on the top, but this is the stress due to tension, stress due to compression. What do you know? You don't know what this is. This stuff is your next course, not dynamics, strength of materials. Okay? NA stands for the neutral axis. It means that somewhere in the middle, it makes sense, it's not experiencing tension or compression. But when you do beam design, you have to be able to calculate this stuff. And the way you calculate the maximum stress that this beam will experience is the moment that's being supplied on the ends, and the moment is due to the force, right? Everybody with me? You apply a force, and you can calculate what the moment is. Moment times y, it's the centroid of this structure, and then divided by I, which is the second moment of area. So, what are we saying? The maximum stress that a beam would be subjected to is due to the force that's applied, which gives you the moment, times its centroid, which has to do with its geometry, and divided by the second moment of area, which is due to what? Its geometry as well. So not only do you need to know the loading on the beam, you also need to know what the shape of the beam is. Okay? So this is one instance in engineering that you need to know the second moment of area. Okay, so that's a civil example. Now let's do a mechanical example. So let's look at a bicycle wheel. So this is a traditional spoked wheel, right, where the rim is here, and then you have a bunch of spokes. And then there's a center material too. So there's material here, there's material on the side, and there's material on the spokes. What about newer designs, right? They're a disc, right? There's no air in there. So what would you say about the difference between these two? The difference is how you're distributing the mass. The wheel has a certain mass, and I'm not talking about the tire, it's the wheel. The wheel has a certain mass, and it's distributed in different ways. This is more evenly distributed. Where here, the load is concentrated here and mainly here. I mean, this does have, some weight, but it's minor. The distribution here is more evenly. So, we always have to be able to, when we're doing any kind of design of parts subjected to a circular motion, we need to know what the moment is about a point, at any point. And what is it equal to? It's equal to the moment of inertia, and this one has to do with what? Mass or area? Mass. I can't write on here. I guess you should write on here. This is the second moment of mass. That one was the second moment of area. This is the second moment of mass times the angular acceleration, which you worked with in angular acceleration you work with in Physics 4A, and you'll be working with in dynamics. not in statics because things aren't moving. So here's another example when you use the second moment of something. And then I have a third example. I'm not going to talk about that because we're only going to deal with second moment. And this, let me just say that this value of K, so we're talking about column design. This back to civil, right? If this column is very wide, I'm not going to have a problem with buckling. But if it's very narrow and I'm applying a compressive load, it could start to bend, and that's called buckling. And you don't want columns to buckle, right? Look outside, there are columns there. We don't want to see those buckling. So the buckling depends on how slender it is. So the critical stress, this has to do to make sure that buckling, will not occur. This K value, I can't remember what its name, it's coefficient of something, but it is a function of the second moment of area. Okay? So these are three ways you're going to see. Like I said, those of you who are these majors, you're going to be dealing with both of these. If you're this major, you're going to be dealing with only this one. So now, the way you calculate, I'm going to use the terms correctly. I'm going to call moment of inertia the second moment of mass, and I'm going to call second moment of area second moment of area, just so that you get comfortable that you know there's a difference. I'm not going to use the engineering term where I would say moment of inertia, and I can mean both. In order to calculate, so now you know in engineering it is important to be able to calculate that, and there is a way of calculating it using integration. But we're not going to use integration again. We want to be able to look at a composite body and find out what its moment of inertia is or its second moment of area is. So there are derivations. I remember in physics, I don't know for you, they used to the physics professors used to write, do this whole derivation and it might be this long, I'm exaggerating. They start with a derivation here, and they go all the way over here, and then they say, oh, this is the equation you need. Well, I was always happy when we got to here. I mean, I thought the derivation was fun, it's like a puzzle, but in the end, I want to know what's functional. So that's what I'm doing. I'm giving you this. I'm not showing you the derivation. Or I should say, I'm not showing you the derivation on the board. I have it in the packet. I derived the equations, and they're in the packet, and you can look at that if you want. But what I want us to concentrate on now is what is in the box. What is the second moment of area and the moment of inertia for bodies? And the place I find that is in the packet. And it is, so here's all the derivation. Here's all the derivation. So it's in here. Here it is. Does anybody have their packet printed out? Go to page 51. Okay? And what I want you to do is I want you to cross out, put a vertical line through this. So the only thing we're going to be working with can't move it up and down. How come I can't move? Oh, maybe because it's on this. Would you stop? We're not gonna use those weird ones, so let's do this. Oh. All right, let's look at these. So what am I asking you to do? I'm asking you to cross this out. Okay? And why did they take down my little things? Well, you're just going to have to ignore it. So what we're looking at is this. And this is the second moment of area of these shapes. And I'm going to change it a little bit. What do you think this point is?
Center mass.
The center. So I'm going to call this x of c. And I'm going to call this y of c. Okay. What is this point right here? The center. This I'm going to call x sub c. And this is y sub c. Okay? And I'm going to put this here. And then here we have the same thing. Here's c. Here's x sub c. And y sub c. And this is sub c. Yeah, just hang on a second. Okay, so let's look at our structure, let's look at our shape. We have a rectangle. The base is B, right? Right? And, oh, I should go back. When we were looking at the wheel, the idea of the wheel, when we're dealing with whether it's second moment of area, or moment of inertia, moment of inertia is distribution of mass, right? What's second moment of area? Distribution of? Second moment of area is distribution of? Area, right? Moment of inertia is distribution of? Mass. Second moment of area is distribution of? Area. Do you remember what the physics department did when they were showing you, demoing you moment of inertia? Weren't they spinning stuff? And depending on where the weight was, like if the load, if they had a string, use that damn thing. Here's the body, and if I'm spinning it here, right, versus spinning it here, right, it's distribution. The further, think of it in terms of moments. Sorry, I'm getting hot. If I have a greater moment if I have a longer lever arm, right? So if I'm trying to turn a bolt, and I have a small wrench versus a big wrench, which one's going to give me a greater torque? The longer one. Which is going to give me a greater moment? Same, the longer one. The longer the distance, the greater the moment. And you could think of that in terms of moment of inertia too. The further I am away from the body, the greater the second moment of area and the moment of inertia is. Okay, could you think about that? That you know that, right? The greater the distance, the longer the load is away from something, the greater the moment, right? It's the same in second moment of area or moment of inertia. The greater the distance you are from something, the bigger the moment of inertia is, or the second moment of area. Let's not talk about, well, why is that? But let's just realize that that's the case. I'm talking a lot and we have to do a problem. Alex.
Well, I'm just wondering, if you have a greater moment of inertia, it's harder to spin that object, right? But, why is it that
Let's not do a why question, because a why is really the science. Let's do the how, because that's the engineering, and we can talk about it some other time. Okay. Okay. So when we look at this body right here, we have a base of B and we have a height of, where is it? Is it H? Mm-hmm. Yeah, H. Okay? So the second moment of, what am I dealing with? Area. You see it written here? Second moment of area. My second moment of area about this axis is BH cubed over 12. So B is whatever this distance is, and H is whatever this distance is, cubed divided by 12. Okay, just like take that. What about if I found this value? How would I solve for that? in this case, I'm trying to find, this is the distribution of area. Oh, actually, which is going to be larger, you guys? Is the distribution of area about the XC axis going to be greater, or is the distribution of area about the Y sub C going to be greater?
Why?
Tim, why?
Because there's more of it further away.
It's further away. Remember I said that the thinking, moments, the further something is away, the greater it's going to be. Look at this. There's a lot more material here further away from the Y than the material that's the distance from the X. Okay? So how am I going to calculate it? The standard equation is always, for rectangles, is BH cubed over 12. That's the equation. When I look in this direction and I'm looking at the x-axis, my base is this value right here, which let's say is 4, and let's say this is 2. B, this would be 4 times 2 to the 8th divided by 12. But when I look at the y, I have to tilt my body, because I'm trying to find, it's like as if trying to find my spin over this. This now becomes my b. It's 2 over 4 cubed. So what equation do you have to remember? BH cubed over 12. For a rectangle, BH cubed over 12. If you're, damn, I just got purple. Put your arm like this. If this is the axis you're trying to find it about, where's your B? B is parallel to that axis, right? But if you're trying to find it about, if you're trying to find the second moment of area or mass about this axis, where's B? B is always the axis that's parallel to it. So when I was trying to find it about the x-axis, before is B. But when I'm trying to find it about the y-axis, 2 is B. Got it? Okay, let's do the next one. Now we have a triangle. The equation is BH cubed over 36. Okay? So let's do this. Let's say this is, again, 4 and 2. So how would I calculate this? B is 4. H is 2 cubed over 36. But now, when I do y sub c, the equation is still BH cubed over 36. But now B is not, what is B? 2. And what's H? 4 over 36. Okay, how about for the circle? Let's say the diameter. Have you guys, phi is diameter. Let's say it's 4. It's equal to pi r, which would be 2, to the 4 over 4. What about ix, I to the yc? Same. Okay, what am I calculating here? What do these values represent? The second moment of area. It's this, but we didn't have to do integration because it was derived for us. And, let's pull this down for a minute. But there are other shapes, right? All our bodies that we design in engineering aren't always just these 3 shapes. There's a semicircle, there's a quarter of a circle, and then there's something that we hardly ever use. Pizza, that would be nice, right?
Introduce the pizza.
Okay? Okay, so now, one more piece before we can do a problem. Let's go over all the way over here. So, we have a rectangular body, and we now know, good. We now know, that's no good either. I should just use my other ones, they're more environmentally friendly. BH. So what's I represent?
Second moment of area.
Second moment of area about the XC axis is equal to what? BH cubed over 3. So this is, let's say, 5, and let's say this is 10. It would be 10 times 5 cubed over 3. What units is it in? What units is this in? Let's say this is inches. I don't know. What is it? It's unit of length times to the 4th. Length to the 4th. Do we always want to find the second moment of area about the centroid of a body? No, because in engineering, I'm going to combine this shape with this part with, another part like this, and, they might be all over the place. So I need to be comfortable finding the second moment of area about any place. So how do we go about doing that? There's an equation. So let's say